Our next speaker is Shreyas Skandan from the University of Penn from the Grass Laboratory.
All right, so a little backstory. So I'm a first-year PhD student at the University of Pennsylvania. I did my master's there in robotics, and I worked there for a year after working with CJ Taylor and Vijay Kumar. Most of my research is focused on computer vision and obviously deep learning, and mainly focused on stereo vision cameras for robot perception tasks. So what this talk is going to be about, trouble with this. Okay, this talk is going to be about me, and okay, it's supposed to switch to the next slide, and drones, and GPUs. So I'll try to keep it more about drones and GPUs and less about me. So I'm going to try and cover all these topics, but mainly it's going to be focused on the DARPA Fast Light Autonomy Challenge. It was a 3-year project, and I joined roughly in the second year. It was basically, the task was to design a complete autonomy software stack that could work on commonly accessible hardware. So we had a lot of design challenges in terms of hardware and software, and the NVIDIA TX2 was a critical component on how we put everything together. So in the hardware section, we're going to talk about how we made best use of a really small payload, and how we designed the open vision computer that integrates the Jetson TX2 into our platform. And in terms of software, I'm just going to run through a couple of software stacks that work comfortably on the TX2. And if we have time to look ahead at some of the future work that our lab is doing. Like I mentioned, the DARPA FLA challenge was basically, you want high-speed autonomy in a really small UAV platform with no GPS. And we're talking about upwards of 20 meters per second in moderately to low cluttered environments, and we can do about 5 meters per second indoor in highly cluttered environments. And so over the 3 years, we shrunk our platform down from 450 mm, which is tip-to-tip span, to 250 mm. The first platform used an Intel NUC. It had a Velodyne LiDAR. It had all the bells and whistles, but that was too big for us to fly indoors. And DARPA said you need to make it smaller and smaller and make it do what it was doing on the big platform in a smaller package. One of the first things we did was to get rid of the Intel NUC and the LiDAR. LiDARs were really expensive, and we broke a couple of them, so we'd like to not to do that. So how do we make use of a small payload? Like I said, we were using an Intel NUC, 2 point-array cameras for stereo, a vector nav IMU, and then our first platform had a Velodyne 16-beam laser. We eventually switched to a nodding Okuyu, as you can see in the top image, but then DARPA said make it even smaller. We need this thing to go through windows and doors. So the first thing we got rid of was the LiDAR, and then we started thinking of ways that we could integrate our hardware and software into something that would be more robust than having a bunch of USB 3 cables dangling off of our drone. It doesn't do well to having rotors fly past it every couple of seconds. And so to replace the LiDAR with something that may not be as accurate but could give us the enough information for our mapping and planning algorithms. And at the time I was working on my master's thesis was to look at what kind of dense stereo algorithms could work on embedded platforms, and could we leverage the GPUs for such a thing, because people have been using GPUs in stereo depth estimation for a while. But could we get it to do high resolution depth estimation on board something like the TX1 at the time? And then we also wanted as tight synchronization between all our sensors, because our entire state estimation stack really needs tightly synchronized data. And we also moved to a time of flight camera for our indoor environments, just trying to fuse all these different sensors in the different environments that they're good at. And you can see our resulting drone is the one at the bottom. It might not look very aerodynamic, but it did exactly what it needed to do quite successfully. So then came the question of how do we integrate everything in a very synchronized platform in terms of hardware. So we eventually got all of our stack working on the TX2. We actually used the Connectech Orbity carrier for our transition from the Intel NUC to this platform, and it was great for us. But then we started talking with Morgan Quigley of Open Source Robotics Foundation, and he designed the Open Vision computer for us. It's basically an integrated compute and sensing unit that has an FPGA, an IMU, all tightly synchronized around the TX2. So this is what in red was the prototype version of the Open Vision computer, and on the right is the current revision where it's at. So we have a TX2 that sits on this compute plate, which is connected to a sensor plate on the front. And these things can be swapped out if you don't want a stereo baseline, if you just want a single RGB camera, you can just switch out that front sensor plate, and you should be able to run our entire software stack on it and add your own. If you've been working with TX2 software, it would just be compatible. And so that's just a brief overview of how we built this piece of hardware specifically tailored for robotics and mainly so aerial vehicles. It's small, it's lightweight, and just going back to this, we often fly it without the heatsink because quadrotors have 4 fans. Right? So like I said, we now have a really tightly synchronized piece of hardware. But how do we make best use of everything we've got? Adding the FPGA can do at stream rate computations, but programming an FPGA isn't as easy as writing something like CUDA, which is more developer friendly. So right now we do very simple tasks on the FPGA. So for our state estimation, we do stereo feature matching, and that we detect these features on the FPGA using fast corners, and that's done at stream rate. On the GPU, we do deep learning, dense stereo depth estimation, calculating image pyramids for tracking, and the rest of our planner is usually on the CPUs. So the back end of our state estimation, along with mapping and then the basic controller commands, is done on the CPU. And there's a table of roughly how much computation each of these requires, and the TX2 has been able to do all of this comfortably. So like I said, the FPGA, that it spits out a set of features. That's a picture of Morgan Quigley, who built the Open Vision computer for us. And this is state estimation working at, on the left is a 20 meters per second flight trial, I believe. This is some of the work that I did, was looking at dense stereo depth estimation. It's a lot of GIFs, but I can walk you through it. So on the left of each is the grayscale image that we work with, and at the bottom is the corresponding right camera image, and the colorful point cloud are real-time results from the TX2. At this time, it wasn't the Open Vision computer. This was running on an Orbity, the Connectech Orbity carrier, and we can roughly do about 8 frames per second on a roughly 1.3 megapixel image at about 128 disparity levels. So we might not be able to get as accurate readings as a Velodyne, but we've been able to get a pretty good sense of layout, and you can see that the tables and chairs show up very nicely, so it handles small objects too. And all this runs real time on quadrotor platform.
That it? Yeah.
Yep. Right, so this is the entire phase of our final mission for the Tampa FL challenge. So all you had to do was give the drone a very high-level goal, saying you're starting from here, you need to go to this location free of GPS. It's the building, wherever the final endpoint is, 100 meters ahead of you, and at some elevation if you wanted it to go enter through a different flow. So here we gave it a waypoint inside the first flow from outside, just by just guesstimating 100 meters ahead and possibly 20 meters in elevation, and the drone entered by detecting which window was open, and it flew down the corridor, and we set a threshold on how much exploration and mapping we want to do because we have a limited battery life. So this run, I think the drone explored 2 windows before it decided it needs to start looking for a way out. And then we have the drone now descending the staircase before it eventually makes its way outside. So this is completely autonomous with just high-level user commands. And yeah, this is where the UAV finds its way out. And this is the entire state estimation stack running on the drone. This is just playing back all that data inside ROS and Arbis, if you're familiar. This is the drone finding its way out of through the corridors, and this is our planner working in real time. So it's given a set of consecutive goals saying you need to go here in this next step. And like I said, this is completely autonomous, running in real time, with the TX2 being the only source of computation, except for the features coming in on the FPGA. Right, so that was basically the entire software stack and how it came together, and the cumulative end to that project. And these are some excerpts of different pieces of autonomy and intelligence that we built for the drones, like trying to detect what kind of windows are open windows and closed windows. So if you can see, DARPA made it harder for us by putting black boards on windows. So just naively looking for dark rectangular spaces didn't help. So we needed to use depth as a way to reaffirm our sense of which window is open, which window is closed, and even navigating through those corridors was a pretty challenging task. And at the end, DARPA gave us this building that's to simulate a destroyed building and to test our autonomy stack there too. So we just gave the drone a waypoint somewhere inside this area of rubble, and it's highly cluttered. And even though our platform, by the end of it, was designed more for indoor settings because we're using a time-of-flight camera, and that doesn't do very well with natural light, it still did a very good job of autonomously navigating through all that rubble and missing, doing pretty good object avoidance as well. So looking ahead, so that is basically how the TX2 became the center of our compute platform. And then we've now started looking at more features that we can add to this autonomy unit that we've built. And some of the things we're doing now is our lab is now looking at a lot of multi-robot coordination. So this is some of the work I did with a PhD student who's just about to graduate, where he's trying to make a bunch of drones work together by just guessing where each other are in 3D space. So here we're running a deep learning algorithm for semantic segmentation that was based off of ERFnet. And it does pretty high resolution semantic segmentation, which is pixel level classification at 640 by 512 image resolution. So on the left is a grayscale image of 2 drones flying inside our lab, and the middle image is the detected mass of each of these drones. And on the right, we've also experimented with indoor semantic segmentation. So for our UAV to figure out what's what inside like an office space. This is actually some of our classroom spaces. So it detects the floor as the yellow color, and the green is a door, and the ceiling in pink, and the walls in red. So it's very coarse right now. What we can do in real time isn't the state of the art in segmentation in the deep learning world, but we can get some of these really sophisticated networks to work on real time on our UAV platforms. Some of the work that also we're using the TX2 for is in the space of event cameras. So event cameras are bio-inspired and they detect changes in intensity rather than the intensity itself. So this is some work done by Alex from our lab. If you're familiar with fidget spinners, that's an event camera tracking the fidget spinner in low lighting. So it does really well in dark environments, and so it runs around 50 milliseconds, this deep learning algorithm on a GTX 960, but we've flown this on our Orbity carrier TX2 at around 10 to 15 hertz, and we got the same results. This is some work that he's also done in event camera-based depth estimation, also running on a 960, which is a laptop-grade GPU, but it also runs at around 10 to 15 hertz on the TX2. This is some of the work that I've been part of we have a precision agriculture team that's looking at trying to help automate some of the agriculture problems. So we've been looking at yield estimation and fruit tracking with our UAVs. This algorithm does not run on our drone platform yet, but this is one of the first things we'd like to try with the Xavier. I believe just looking at the numbers from today and the spec sheet, we should be able to get our detection and segmentation algorithms to work on real time on the Xavier, but some of our 3D mapping and tracking is better done post-processing. Looking ahead for Penn and this autonomy stack that we've built around the TX2, Penn is now part of the DARPA Subterranean Challenge, where we're to build a heterogeneous robot systems for underground operations, again with no GPS or even just plain communication is difficult underground, so you can think of like mines and environments like that. And we need a system that can traverse through large corridors up to and greater than a kilometer. So the Jetson TX2 is definitely going to be part of this platform right now, and we're already looking at ways to integrate the Xavier onto our platforms. We're going to be working with Exyn Technologies and Ghost Robotics, who also use the TX2, and currently looking at the Xavier. So I'm happy to talk to anyone if they've got ideas about how to better use the Xavier and the carrier boats for our platform, because now we're working with ground robots and much larger UAVs as well as our small indoor UAVs. That's it for my talk. And thank you to NVIDIA for having me down here to talk about some of the work that my lab is doing. Thanks. If anyone has any questions about how we integrated TX2 onto our UAVs, I'm happy to answer some questions if there's time.
Any questions for Shreyas?